Space is stretching right now, even between your eyelashes. The immediate takeaway is simple: your coffee cup is safe. Local forces beat cosmic expansion by an absurd margin. That stretch is real space growing, not things pulling apart. So bound stuff ignores it, like a boat ignoring tides. Gravity, electromagnetism, and pressure keep structures locked together. Across a meter, expansion adds about 0.06 nanometers per year. Your skin's molecular bonds laugh at that tiny nudge. Weirdly, on the largest scales, expansion absolutely wins. The trick is knowing where each side dominates the game. Let's map that boundary, from atoms to galaxy superclusters. Picture distant galaxies drifting apart like dots on rising dough. Space itself is growing, stretching the distances between unbound objects. If that growth dominated everywhere, structures would slowly unweave. Here is the key idea called metric expansion. Velocities scale with distance, set by the Hubble parameter today. That parameter is about 2 times 10 to the minus 18 per second. So nearby points hardly move, while far ones drift noticeably. Across 1 meter, the added speed is unimaginably small. Multiply that by a year, you get about 0.06 nanometers. Across 1,000,000 parsecs, you get roughly 70 kilometers per second. Rule of thumb, double the distance and the speed doubles. But bound systems do not follow this gentle flow at all. Gravity and other forces override the stretch inside their domain. Mathematically, their potential wells decouple from the background growth. Example in real terms, the Milky Way ignores expansion completely. Its stars orbit the center, held by a massive dark halo. Bottom line, expansion acts like a whisper next to local shouts. Zoom down to an atom where electrons haze around a tiny nucleus. An atom stays whole because charges attract and quantum rules quantize motion. If expansion tried to pry it, the bonds would snap back. Why care? Because your body is made of these stubborn systems. The forces here are enormous compared to cosmic nudges. At the Bohr radius, the electric pull is breathtakingly strong. An electron there accelerates near 10 to the power of 23 meters per second squared from the nucleus pulling inward. Contrast that with expansion across an angstrom-sized distance. The added acceleration is about 4 times 10 to the minus 46. That difference is madness, over 69 orders of magnitude. Even molecules vibrating at room temperature shrug the effect away. Chemical bonds sit in energy valleys with walls around them. Expansion is like gently tilting the table by 1 atom. Nothing spills because the walls are many trillions times higher. Net result, atoms and molecules ignore the universe's slow stretch. Now stand at the edge of the solar system, among icy comets. Orbits there still circle the sun, barely feeling cosmic expansion. Bound orbits persist because gravity crafts a deep potential well. If you drop a rock, it falls back into that well. That is the whole game for planets, moons, and comets. There is a helpful yardstick for bound size around a mass. Take the sun's gravity, compare it to the background expansion rate. Compute a balance radius where stretching and binding roughly tie. It scales like the cube root of gm over h squared. Plug numbers for the sun, you get around 20,000. That is 1/10 of a parsec, comparable to the inner Oort cloud. Inside that scale, expansion loses absolutely every single round. Planetary orbits process a little, from planets tugging on planets. But they never unwind because cosmic stretching is too faint. Stars stay bound to clusters for similar reasons, just bigger numbers. Gravity there crushes the background's whisper by many orders. So the picture is simple: orbits beat the cosmic drift. Shift to a galaxy core glowing, wrapped in a faint halo. Galaxies hold together inside invisible cocoons of dark matter. Those cocoons are massive, and their gravity dominates local dynamics. Care matters because without halos, stars would drift into space. Here is how a halo keeps the galaxy sovereign. Dark matter collapses early, then virializes into a stable distribution. Stars form later inside the well and orbit within it. The net binding energy dwarfs the background expansion by absurd factors. Use the same balance radius trick, but with 1 trillion suns. The number lands near half a megaparsec, about 1.5 million light-years. That roughly matches the realm where the local group stays together. Beyond that, expansion carries unbound galaxies apart along filaments. Inside, stars and gas ignore the stretch and follow the halo. Tiny test: remove the halo, the rotation curve collapses instantly. Bottom line, halos are umbrellas that block the cosmic rain. Inside a star, matter hisses, pushes back, and holds shape. That balance is called hydrostatic equilibrium in simple terms. It matters for stability because otherwise stars would implode fast. Gravity pulls inward, pressure gradients push outward across every layer. Energy from fusion sustains the push in normal main sequence stars. When fusion stops, quantum rules add a new shoulder to length. Electrons or neutrons fill levels and resist being packed tighter. That resistance is called degeneracy pressure, and it is fierce. Central pressures are overwhelming by human standards, think 10 quadrillion pascals. Compare that with expansion trying to stretch a star across itself. The added pull is effectively zero on any realistic timeline. Even white dwarfs and neutron stars stay compact against the background. So the picture is clear: pressure partners with gravity to hold. Only extreme tides near black holes can rip these bodies apart. Cosmic expansion is not that kind of tide at all. Net result: internal pressure makes stars utterly indifferent to expansion. Planets behave the same way, with materials pushing back under compression. Step back to the fabric itself, driven by a strange background. We call it dark energy, a uniform energy density in space. It matters because it accelerates the expansion, changing cosmic fates. Best measurements say its pressure equals minus its energy density. Physicists summarize that with a symbol W equal to -1. That case acts like a built-in cosmological constant term. Under that case, bound structures remain bound forever in principle. Accelerated expansion just makes unbound regions drift away faster. There is a spicier option called phantom energy, with W below -1. Then the density grows as space stretches, feeding on the future. In that scenario, even galaxies, stars, and atoms eventually unbind. Timelines vary, but the last moments look frightening and quick. Planets peel off first, then stars, then molecules, then nuclei. Data today do not favor that path within current uncertainties. A simple reading gives W around -1 within a few percent. Current best fit, W is about -1. Bottom line, dark energy speeds separation, but it does not shred. Hold your arms apart and wait, nothing stretches them in your lab. That is because expansion is almost perfectly uniform on small patches. Uniform change adds no stress, only gradients can pull things apart. Galaxies create far stronger gradients, and they set the rules. The expansion field inside a bound region mostly cancels itself. Only a tiny residual tide remains from the external background. Across 2 meters, that tide is around 10 to the -35. Meanwhile, the moon's tide on you is about 1 micro-G, 9 orders bigger, and you cannot feel that one either. So everyday materials never notice the universe's background stretch. Net result, tides you feel come from nearby gravity wells. Now pan across the cosmic web, filaments glowing like ember trails. These strands and nodes are places where gravity already won. That matters for our future sky and for our address. Over time, bound islands tighten, while voids widen like oceans. Halos merge into bigger halos, and clusters merge into superclusters. Unbound neighbors fade away, redshifting until their light hides beyond reach. Example you can picture: Andromeda and the Milky Way collide. That happens in about 4 to 5 billion years. The local group likely relaxes into one giant elliptical remnant. Far away, the Virgo cluster will drift further and further outward. In trillions of years, only our island remains visibly lit. Rule of thumb: dense regions decouple, sparse regions evacuate into darkness. Bottom line, the cosmic web is stitched by self-gravity, not glue. So yes, space is stretching, even inside your room today, but your coffee cup stays whole because local forces dominate. From atoms to halos, binding winds on every meaningful scale. That was the quiet secret keeping the universe from tearing apart. If this cleared the picture, join me for more space stories. Bottom line, our sky stays whole because binding always wins.